All right, so we have on number, what is this? This is number 19, but I don't know where.
4.2.
4.2 probably.
4-point question mark, number 19.
Sure.
We have two identical tanks, T1 and T2. Oh, this is going to be hard because now it has to be identical. Pretend those are identical.
Too curvy on the bottom.
Okay, that's T1, that's T2. And they initially contain W gallons of pure water.
W.
W for water. W.
Oh.
And that's really the initial, right?
It's like W plus a 10 W.
W gallons initially. W gallons initially. Okay. Then, starting at 0, a salt solution with constant concentration is pumped into C1, or into T1. Okay. Concentration C. Salt. At R gallons per minute. R gallons per minute. The picture, by the way, is kind of clutch for these. Like, spend some time labeling your picture. It's really kind of the hardest step at the beginning. And drain from T1 into T2 at the same rate. Okay, so that means that this goes there, R gallons per minute. Do you know the concentration there?
Nope. It's just A over something plus something, and then minus
yeah,
something?
it's like A over some amount. Okay, we'll figure it out. But question mark concentration for now, not stated at least. Then it says, the resulting mixture from T2 is also drained at the same rates, and presumably they don't do anything with it. So, I guess we just assume that R gallons per minute of salty water dumped on the ground or whatever. And then we're supposed to find the concentrations in the tanks for time bigger than 0. Okay, so my goal is find C1 and C2. So first, it's a tank problem, right? So what are you actually going to write differential equations for?
The amount.
The amounts, right? So C1 is going to be the amount in tank 1 divided by the volume of tank 1. Right. And C2, the concentration in tank 2, that's going to be the amount in tank 2 divided by the volume of tank 2. Okay, so let's tackle some extrapolation things. What are the units on the initial concentration that's coming into the tank?
Probably pounds.
Yeah, probably pounds. Some kind of mass, probably, of salt. Per what?
Gallon.
Liter.
Hopefully in gallons. Right, if it's not in gallons, you need to go apply a unit conversion to this thing first.
That's great.
You were wondering he's from Oakdale. Money trap.
Figures. Alright,
We should just do that now. It's fine.
so
Start filing.
I have a concentration C units of mass per gallon and a rate R gallons per minute in here. What's the volume of this tank? So what's V1?
Pi squared H.
Pi squared H. Why do you assume it's a cylinder?
Because it looks like a
It
cylinder.
could be a dodecahedron.
Why does that
What
look
is
like
a tank? I would assume it's a square.
It's-
Why I assumed it was a
there's-
cylinder.
What?
That's a real
Okay,
process.
at any rate,
Water.
it doesn't matter what shape it is, it's identical to the other one. But how much water is either being added or subtracted per minute?
W plus R?
R.
Oh, W plus R minus R2.
What?
We should. There
What?
should be different labels.
0.
No, there should not be different labels.
Why
The
not?
rates are all the same.
Oh, they're okay. Okay.
They very specifically are all the same R.
There should always be.
That's a
W gallons.
feature, not a bug. So, this volume, right, starts at W gallons, and then every minute you add R gallons and take R gallons away. So it's W.
Right.
And then over here, volume tank 2,
W.
also W. Same reason. You're adding R gallons a minute here, and you're taking R gallons a minute there away.
Right.
That's good with that? Okay, good. So I can replace these. I now know that those are just W's. That's something. Then I need to know about the amount in tank 1, right? So what do I know about the amount? Do I know the amount actually, or do I know something related to it?
The quantity, sort of. Yes, maybe. No.
Isn't the amount also
Well, no, the
So,
amount is
amount of salt, right?
R by 1.
Okay, so I think I
R
know.
by C, CR.
I'm gonna find out about dA1 dt, right?
Sure.
So the rate at which the amount of salt in the tank is changing is the always do
CR.
this. All go the same way. So you were asking for general procedure?
Yeah.
These ones at least all go the same way.
Mm-hmm.
The rate of change of stuff in the tank, right, the amount of stuff in the tank, is going to be the
CR.
rate in, concentration in, minus
Yep.
rate out.
So-
concentration out.
rate in R gallons per minute times concentration in, that's C masses per gallon. Gallons cancel, you get a mass per time. That checks. Crap. On the way out, it should be a rate and a.
A over things net, which would be 0, which would be 0.
Okay, so first things first. It's a rate and a concentration, right? Which of those is easy?
The rate.
R.
The rate. It's R gallons per minute. And then I never filled in my concentration here. So right now that's the question mark I have there.
That's when you get the A over.
The
Yeah, and the concentration in this tank is the amount of salt in the tank divided by the
volume.
volume. What was the volume?
V.
Double.
Close up.
That's good with that? Okay,
Oh,
so,
because R is the same. Gotcha.
and then that's the one for the first tank, and then the second tank, dA2 dt,
Isn't that like the same thing?
is
Except swapped.
Except you're just gonna have an A2 over there.
Oh, but the rate, the concentration in is the out of the concentration previously.
good. The
Oh,
concentration
right.
into this tank is really just flat the rate of amount in, right? Is just what that other tank was losing. Right, so you just take this part, put it down here. So you get RA1 over W. That really is just
Gotcha.
this dude, right? That tank's losing it, this tank's getting it. And then I'm subtracting something, and what am I subtracting?
Out.
RA2W?
Okay, R, and then A2 over W. Right, the rate out, and then the concentration in that tank is A2 over W. You guys see that? So this gives me two equations that I have to solve. I have dA1 dt is RC minus RA1 over W, right? And dA2 dt is RA1 over W minus RA2 over W. And then you're like, whoa, dude, how do you solve that crap?
It's
They do
separate.
in terms of each other.
You just
No, it's
back
Yeah,
it
they're
up,
all
so-
like in terms of each other or whatever, right? So
Good assistant.
it's actually not
Congratulations.
quite true.
That one's independent.
This one's in terms of that one. This one's actually all just in terms of itself. You see that? If the tanks were interconnected, then you'd have a bigger problem here. Does that make sense?
True.
Like, because these two tanks are in a series, it's actually not so bad.
Well, so the tank
Oh,
2
God.
is only getting stuff from tank 1.
Yeah,
Two tanks
and
in parallel.
the first tank is getting this constant input, right? It would be weirder if there were stuff coming into this tank and then the two tanks like swapped some stuff. Like that would make things more complicated. We'll do those later, but
Oh god.
Like if tank 2.
they're actually, I'm saying they're complicated, they're really stupid easy with a little bit of linear algebra.
What if tank 2 drained back into tank 1? Problems?
Well, that's what he's
No,
saying.
just, it'd be more complicated. We'd need a little linear
Just get
algebra.
like a third term on each, and then you need to.
It's like matrix problems.
Yeah, there'd be another input, right, so you'd have another term. And then, yeah, you just set up a matrix differential equation instead of a regular one.
Yeah,
And they,
simple stuff.
Let's take the
they actually are easier, not harder, which is funny, but anyway. I'm here back in the land where I don't have linear algebra in here yet. I just need to solve this thing, right?
Yeah.
So, check this out. That's
Slap a D, slap a negative A.
dA1 dt plus R over WA1 is RC, right?
First order linear
That is first order linear,
non-homogeneous.
So it's the
order.
guessing one,
non-homogeneous.
where you slap zeros
Variation
on it.
parameters.
Yeah, this is going to be a variation of parameters problem. I think I can guess that A1 homogeneous,
A sub 1 sub homogeneous.
A1 sub H, is e to the minus
RT.
integral of R over W dt,
Which is easy.
which is chill. So I got e to the minus RT over W. And then what do you do?
You like
Go with.
You guess with some U.
Just move on.
Good?
U equals that times.
So you guess A1 is U times
Can't you
that,
say
right?
y prime times,
And then you.
or
Yeah.
y prime times y homogeneous is equal to the other stuff.
Oh, things just cancel out and you just keep going.
Yeah, this should be relatively chill. So I'm guessing A1 is U times the homogeneous solution. And then I'm like, okay, so that means that A1 prime is U prime e to the minus RT over W
why this RT? You know,
minus R over W U e to the R e to the garbage that I can't say. Yeah, and then you're like, okay, so I'm going to take that, I'm going to plug it in here. So I'm going to get U prime e to the minus RT over W minus R over W U e to the minus RT over W plus R over W U e to the R. Ah, crap, I forgot a minus sign when I said that. Whatever. That shit.
Good enough.
It's going to cancel. And equals RC, right? So that junk cancels.
Find you.
So you got
and
U prime is RC e to the RT over W,
And that's pretty easy.
which is pretty chill to integrate.
WC e to the RT over W.
So you get U as WC e to the RT over W. And I'm totally trusting Chris on that U substitution. Pretty sure that's right.
If I use the W,
W substitution. Oh my god, what do you even substitute? There's already a U and a W.
I know.
How about
You have to do something crazy like triple U substitution.
how about lambda or phi
Oh,
or rho?
Triple U.
How about gamma? We learned how to write
whatever.
gamma today.
Like-
my signature.
Gamma, Joe.
Okay. Anyway, I found U is this thing. What do I do with that information?
Slap it into the
Plug
other
that back
thing.
in, correct.
Yeah, slap that back into A1, right? So I found out here, after all of that, I got A1 is, oh, what'd you forget, Chris?
What did I?
C.
what?
C.
Yeah, there's a constant,
damn
right?
it. Ah.
You deserve
You
it.
lose.
So I got
I should lose.
WC,
Okay.
and then when you multiply here, those are gonna cancel, right?
Oh, that's
So you
fine.
get WC plus
Plus KE.
Ke to the minus RT over W. And then you give yourself a little sanity check, right?
Things should be shrinking or growing.
I mean, you could take the derivative and check.
Kind of think about this and be like, okay, so as t approaches infinity, right, as time tends towards infinity,
Concentration approaches K.
this part is going to tend to,
K.
Big, small, 0.
Oh, infinity. Sorry.
Wait, if it gets towards infinity, it
Zero?
will go towards.
so as t tends to
Oh, it's
infinity,
negative, so it goes towards 0.
right,
so it
this will
goes towards
be
1.
e to the minus infinity roughly,
Yeah,
right?
yeah.
To be like 1 over e to the infinity. So that'll be a really, really small number, which you're then multiplying by some fixed constant. So this piece will go to 0, and you'll get w times c.
Wait, it'll go toward k, yeah? Because you get 0 in the e, and e to the 0 is 1,
Well,
and
if it's
1 by
approaching
k.
zero-
No.
Zero
You get
times k.
infinity in the exponent.
You get negative infinity.
Yes.
So it's 1 over.
So you get k over e to the infinity.
This is really just K over infinity.
Oh, you're right, you're right.
Which is like
Nah.
k over infinity. Which is
Double
basically
zero.
0.
What is that?
Why aren't your infinities connected like all of these?
I don't know, sometimes they are, sometimes they aren't. Okay, so that part limits to W times C. Does that make sense? If you think about it over here, right? W is the amount of water in the tank,
Sure.
and your inputting water at a concentration C, right?
Right. So it's really just gonna be a mass.
Yeah, so eventually it'll just end up like what you're putting into it.
Yeah.
Does that kind of make sense?
Eventually it'll all drain out. You're left with.
Yeah, eventually all the water that you started with will be gone, and the only thing that'll be left is water that you put into it, and you always put in water at a concentration of C. So the amount in the tank is always going to be W times C.
Sure.
Right? Or at least it's going to tend there. Okay, so that's this guy. And we can figure out, really, we could use our T as 0 to calculate this. Right? So when T is 0,
E is 0.
I have-
1.
oh, how much salt was there in the tank at T is 0?
Nah.
None, right? So 0 should be WC plus K times 1.
So K should distinctly be negative, but
Yeah, so K is minus WC. So A1 as a function of T, right, is WC minus WC times e to the minus RT over W.
which matches the formula they have in the book.
Yeah, and there's some kind of reasonable, like, okay, so this is the ratio of the flow rate to the tank size, and then it's an exponential decay. That kind of makes sense. What's that? And this is kind of how much salt it was short of what you would expect it to be. Okay, so that's the first one. How do you do the other one?
Plug it in.
Yeah,
Rinse and repeat.
take that, plug, right?
Rinse and repeat.
So you get dA2 dt is R over W
RC
times WC minus WC e to the minus RT over W minus R over W A2.
You could simplify that a little bit.
And then you're like, okay, so we'll slash some W's at least. So we get dA2 dt plus R over WA2 is RC minus RC e to the minus RT over W.
Which is also easy, but now harder.
Yeah, which is essentially the same problem, but slightly harder. So let's see if we can remember how we did the other one.
Well, then we have 1 over R dA.
Okay, so what do you need?
Homogeneous.
Variation of parameter.
Yeah, go get the homogeneous solution. What's the homogeneous solution look like?
E to the negative RT over W.
Integrated.
Yeah, it looks like the same friggin' thing, right? So you're like, alright, so A2 homogeneous is e to the minus RT over W, right? Same thing?
And then we just, call A prime what it is. because
Okay.
we-
And then we already did this step earlier, right? So we're like, alright, so A2 homogeneous prime is U prime times e to the minus RT over W
Wait. it's not
minus
homogeneous anymore, though.
R over W U e to the minus RT over W. What did I screw up?
It's not homogeneous.
it's just
homogeneous
A prime.
anymore.
Oh, thank you. It's A2 prime is this. I skipped a step.
That's fine, we know it.
A2 was U times e to the minus RT over W. Good? Okay, then what?
Plug and jug.
Plugsies? Okay, so those are going to cancel again. So I got U prime e to the minus RT over W. Right? Equals
That matters.
Everything else.
RC minus RC
E to the negative RT over
e to the negative RT over W. Then what?
Your E thingies cancel.
U,
And you really
Maybe.
just get
find U.
RC e to the
So you get U prime is
RC e to the RT.
RC e to the RT over W
Minus RC.
minus RC. Cool. So that's U prime. So U is terrible.
Integrate by multi parts.
And you get
No.
CW e to the.
Okay, so there's a minus RCT at least.
You can start out of order, it's fine.
And then this part you do a little triple U substitution.
But do we really?
Wait, where did you?
It's just CW e to the RT over W.
Yeah, it's just CW. E to the RT over W.
Plus C.
Thank you. Plus constant.
Then proceed to plug back into gas.
And then proceed to plug back into your gas. So take this, plug up there. Get A2 is,
Well, that's CW minus RCT.
yeah, so CW e to the RT over W times e to the minus RT over W is just a CW, right? Minus
RCT e to the negative RT over
RCT e to the negative RT over W
plus K times that.
plus K times e to the minus RT over W. And then you're like, wait. What about when T is 0?
Well,
CW?
that really emphasized.
Oh no.
So A2 of 0. How much water was, or how much salt was in the tank at time 0?
K should just be CW. Negative CW.
Stop skipping steps. How much salt was in the tank at time 0? In the second tank?
None.
None, it was pure water. So 0 is, and over here, you got middle term with a T in it,
Yeah.
0.
Got
So
it.
you got CW plus K.
And then
So K is
negative
Something
CW.
negative CW again. You guys see this? Okay. So, notice that looks like
That, but worse.
this.
Yeah, that makes sense.
How are these different?
The middle term.
I mean, it's kind of proportional to time.
Perfect. Why does the middle term matter?
It's dependent on one more thing. Because it's.
Yeah, there's some delay, right? Because it's not connected directly to that first input, it's connected to that first input through a frickin' tank. Right, so the salt builds up in the first tank, and then that spills into the second one, right?
If we added a third tank, would you say that that's like RCT squared?
That would be my expectation.
Oh, and that's gonna be the thing with the infinite tank?
Yeah, so if you want to do the next problem, the one with infinite tanks, my guess is they look like AN is CW minus RCT e to the minus RT over W
RCT.
minus RCT squared e to the minus RT over W
Oh, so it's like
minus RCT cubed.
it's like almost like a Taylor series, but
Yeah, it's kind of a, I mean, it's an infinite sequence of tanks, right? You would expect there to be some kind of infinite series, at least type thing, right? And this is the amount in the nth tank, so my expectation is that this like goes a little bit and then stops. And this is the thing that you'd have to spend a second figuring out. It's minus RCT to something,
To the n.
e to the minus RT over W.
N minus, or n plus 1.
N minus 1.
I think it's n minus 1, probably. And then you do have this minus
yeah.
CW e to the minus RT over W thing here. But my guess is that that number is, or that exponent is an n minus 1. Because I had none of them here, and then I had one of them there, and then my expectation is that I would have 2 of them in the next one. Cool. Questions, thanks.